Chapter 14 was called Measuring Toxins. Once we were introduced to toxins and chemical equations, we looked at going a little bit deeper about if we have a toxin, what information do we have about it, and how can we use that? And really the main focus was on LD50 values, or median LD50. But initially what we did first was I showed you guys a process called dimensional analysis, which was a simple way for us to convert from one unit to another, and it was very useful, especially if the conversion was going to be multiple steps. It was a little weird at first. We were wondering why we were doing this, but it became very useful for not only LD50, but for when we got into the mole and when we got into stoichiometry. It was a quick, easy converting process for us to use. So you should be familiar with how to do that. We then looked at LD50 values, and median LD50 is the amount of a substance that will kill approximately 50% of a test population, right? When we looked at in that big table that they can test it on different animals, the LD50 depends on how it's introduced to the body, whether it's oral or intravenous, and the most important takeaway was that everything is toxic, right? The toxicity level just depends on the dosage. How toxic something is depends on the dosage. Some things are toxic at really high dosages, and some are at really low dosages, but everything has their LD50 limit. The relationships you should be familiar with are that the higher the LD50 is, the less toxic it is, because that means the more of the substance you can ingest before you die. The lower the LD50, the more toxic, because the less you can ingest before you die. I gave you some sample LD50 values here, but we dealt with a larger table during this unit. But some of the problems we looked at was, let's say you had a 150-pound person, and you wanted to figure out how much of a substance was toxic for them. So let's look at something like, let's say ricin. The LD50 for ricin is 30 milligrams per kilogram. Again, what does that mean? It means it takes 30 milligrams of ricin for every kilogram of body weight for the person to be lethal. So it depends on body weight. The more you weigh, the more of a substance you can handle. But this is milligrams per kilogram of body weight, and we have pounds. We went over the conversion. Pounds to kilograms is 1 kilogram for 2.2 pounds. Then we can use the LD50. 30 milligrams of ricin is lethal for every kilogram. You do the math, is 150 times 30 divided by 2.2. You get approximately 2,045 milligrams of ricin. We then looked at how we can count the number of objects we have in a sample if we can't see them, because we can't see atoms. So how do I know how many atoms I have in a sample? So the activity we did was I gave you a brown paper bag full of an object. You didn't know how many there were, and your objective was to figure out exactly or about how many there were. So the way we could do it is if you, number one, mass the entire sample. Let's say the entire sample of these confetti sprinkles is 200 grams. Let's say, because I also gave you a small sample of the item, let's say I gave you 10 sprinkles, and the mass of 10 sprinkles was 2 grams. Instead of just massing one, because we talked about why it would be better to mass more than one of them, is because they're a little bit different. They should hypothetically be the same, but it's better to mass a collective sample and take an average to make sure that you didn't get one sprinkle that was larger or one that was smaller. So if you have 2 grams, and that was 10 sprinkles, and that means each sprinkle is equal to 0.2 grams. And if you have a collective group that's 200 grams, take the total mass and divide it by the mass of 1, and that will give you the mass, or the number of sprinkles you have. So 1,000 approximately sprinkles in that sample. We related this to atoms, but also other objects. And the example I gave you here, because I know we use like marbles and beads, sesame seeds and sunflower seeds, but even if you consider baseballs and tennis balls, if you have the same number of each, because each of you guys had the same number of objects in your bag, but the masses were different because each individual item is different. 1 dozen baseballs means you have 12, and 1 dozen tennis balls means you have 12 in terms of quantity, but each one has a different mass. So of course 12 baseballs is going to have a different mass than 12 tennis balls. This led us to the idea of the mole. The mole is a quantifying unit or a counting unit that helps us group atoms or molecules or units. Particles, essentially. Remember that term particle could mean either atom, molecule, or unit. The mole, 6.02 times 10 to the 23rd, is also called Avogadro's number. And this is the number of particles in 1 mole of a substance. We related it to a dozen. Just like 1 dozen means 12 of something, 1 mole means 6.02 times 10 to the 23rd, or 602 sextillion of something. Okay, that something that we're talking about in chemistry is particles, either atoms, molecules, or units. We looked at molar mass. Molar mass was the mass in grams of 1 mole of a specific substance, and we calculate the molar mass by looking at the periodic table and taking the mass of each atom from the periodic table. So I gave you some examples of how we calculated it here. For water, we have 2 hydrogens. They each have a mass of 1, and then 1 oxygen. Each has a mass of 16, so that total is 18. And the unit for molar mass is grams per mole. This number we can also write as 18 AMU, but 18 atomic mass units would be the mass of 1 individual water molecule, where 18 grams is the mass for 1 mole. Meaning if you had 6.02 times 10 to the 23rd water molecules, the mass collectively would be 18 grams. And you could practice if you want, calculating the molar mass of those 2 other substances. This picture is just showing you what a mole looks like for each of these substances. Again, emphasizing the idea that even though you have the same number of particles of each of these different substances, the amount of space they take up is different and the mass they have is different. We looked at problems that were comparing equal moles, different moles, equal grams, different grams, and figuring out which has more mass and which has more moles. So we'll go through a couple of them now. So in this column, we're looking at which sample contains more mass, 1 mole of chlorine, Cl2, or 1 mole of arsenic. Now, we have to look at the molar mass for each of them. 1 mole of chlorine, and chlorine being Cl2 because it's a diatomic element, has a mass of 35.5 times 2, or 71 grams per mole, where the mass of 1 mole of arsenic, if we look on the periodic table, has a mass of approximately 75 grams per mole. So this has more mass. 1 mole of cobalt, or 2 moles, of aluminum. Cobalt has a molar mass of 59 grams per mole, and aluminum has a molar mass of 27 grams per mole. But we have 2 moles of aluminum, so 27 times 2 is going to get you 54. This still has more mass, 54 compared to 59. 4 moles of water. Water has a molar mass of 18 grams per mole if you calculate the molar mass, 2 hydrogens and an oxygen, versus CO2, which has a molar mass of 44 grams per mole, 2 oxygens and a carbon. But you have 4 moles of water, so that's 18 times 4 would be 72 grams per mole, and then 44 times 3 would be 132. So 3 moles of CO2 has more mass. Which contains more moles? Again, we have to use the molar mass. Cl2 has a molar mass of 71 grams per mole, and aluminum has a molar mass of 27 grams per mole. So which one has more moles of molecules? Well, because each mole of aluminum is only 27 grams, we can fit more moles than 300, so this has more moles. Again, aluminum is 27 grams per mole. Mercury is around 200 grams per mole. So where this is just about 1 mole of mercury, 100 grams of aluminum is way more than 1 mole of aluminum. So that has more moles. 300 grams of iron or 200 grams of chromium. Iron has a molar mass of 56 grams per mole, and chromium has a molar mass of 52 grams per mole. So let's just round it off to 50 and make it simple for this problem anyway. 200 grams of chromium would be about 4 moles if each is 52 grams per mole, and 300 grams of iron would be about 6. So there's more moles in 300 grams of iron. Last thing we looked at were mole conversions. How many molecules do 5 moles of water contain? 5 moles H2O. I need a conversion factor that brings me from moles to molecules. That's Avogadro's number. I know 1 mole of water contains 6.02 times 10 to the 23rd water molecules. If we plug that into calculator, 6.02 times 10 to the 23rd times 5, we're going to get 3.01 times 10 to the 24th water molecules. How many grams does 2.5 moles of copper atoms weigh? 2.5 moles of copper. I want to go from moles to grams, so that's where the molar mass comes in. 1 mole of Cu, look on the periodic table. Copper has a molar mass of 63.5 grams per mole. 63.5 times 2.5 gets you 158.75 grams of copper. How many moles of atoms are there in 70 grams? Now it doesn't say how many atoms, it's how many moles. So it's the same thing. 70 grams of fluorine gas. Fluorine's a diatomic, so it's 70 grams of F2. We want to go from grams of fluorine to moles. We're going to use the molar mass. 1 mole of F2. Periodic table. F is 19, but there's 2 of them in that molecule, so the molar mass of F2 is 38 grams per mole. 70 divided by 38 gets you 1.8 moles of F2. And then how many molecules are present in 88 grams of carbon dioxide? I don't have a conversion that will bring me from grams to molecules, but I can go from grams to moles first, and then moles to molecules. The grams to mole step is going to be the molar mass of carbon dioxide, which is 44 grams per mole. And then the mole to molecule is going to be Avogadro's number. In 1 mole of carbon dioxide, there's 6.02 times 10 to the 23rd molecules. 88 divided by 44 is going to get you 2 times 6.02 times 10 to the 23rd. You'll get 1.204 times 10 to the 24th molecules of carbon dioxide. So you should be familiar with how to do those simple mole conversions for this chapter, and that's where we left off with chapter 14.